All right, hello everyone. Welcome to the USC Capstone Project webinar, and we'll get started with everything right now. So first of all, I kind of wanted to go over what this webinar was. Um, our USC Capstone, our club is a club for high school students interested in neuroscience. And we actually go over, like a journal club, we go over different papers, research papers each week, looking into different types of neuroscience research. So for this capstone webinar, we picked out the six most, not only the most advanced, but also the most motivated and the most uh, driven capstone projects that came out of our club this year. And we are excited to hear from these outstanding students soon. But before I get started, Professor Rust or Professor Winston, would you like to say anything?
Oh yeah. So Move, thank you so much for organizing all of it. Um, I'm looking really forward for the talks. I have seen already like a preview and or the topics, and I'm very excited. And good luck to everyone.
Yes, same. Thank you for having us. Thank you for hosting this wonderful event. I'm also excited to see the fruits of the students' labor. Most of what I've had privy to seeing as well too, but it's a very exciting time for neuroscience research, especially at this stage. So thank you so much for hosting, and I look forward to my continued participation in the program. So good luck, everyone.
Thank you so much. First of all, we'll get started with Shrihith. If you could turn your video on, I'll spotlight you so you'll be the center of focus during your presentation.
Can you hear my audio?
Yeah.
Okay. Good morning, everyone. My name is Shrihit from Bellevue High School. My capstone project is MCON AI, multilingual conversational AI for low-cost early Alzheimer's detection. I would like to thank Professor Winston, Professor Rust, Sun Wu, along with the USC Neuroscience Journal Club for all their help and support. Next slide, please. I would like to give background context and my personal motivation behind this project. When I was a kid, I found out that my grandfather has Alzheimer's disease. I witnessed his struggles leading up to the moment of diagnosis. Similar to my grandfather, millions struggle with Alzheimer's. This allowed me to explore early detection of Alzheimer's. Early detection would allow timely intervention for many, like my grandfather. Over 65 million people worldwide are affected by Alzheimer's and dementia. This number is predicted to rise to 152 million by 2050. Artificial intelligence or AI models provide an alternative with higher diagnosis rates as they identify subtle markers. Next slide. Traditional AI models rely on MRI or PET scans, which are costly and inaccessible. Language impairments are among the earliest signs of cognitive decline in Alzheimer's disease. Speech and text-based AI models allow cost-effective, non-invasive detection while maintaining accuracy. However, the majority of current AI models have binary classification, meaning that they only detect Alzheimer's versus healthy control or dementia versus healthy control. This limits early detection of Alzheimer's disease as it does not identify mild cognitive impairment known as MCI. MCI is a critical stage for timely clinical intervention before significant cognitive decline occurs. Next slide. Research gap. Most existing Alzheimer's detection text-based models are English only, excluding a large portion of the global population. Around 60% of people with Alzheimer's do not speak English as their primary language, limiting accessibility. Models trained solely on English datasets lack cross-lingual generability, performing poorly on other languages. This limitation reduces global applicability and reduces risks and increasing risks of inequality in early diagnosis. Next slide. We are using multilingual datasets in English, Spanish, and Mandarin from 8 Dementia Bank datasets. Dementia Bank is a shared database of multimedia interactions for study of communications in dementia. Multiple tasks across picture description, fluency task, story retelling, and free conversation, along with narrative. These datasets are categorized into 4 categories: dementia or DM, Alzheimer's or AD, MCI or mild cognitive impairment, healthy control or HC. Some datasets focus on dementia, while other datasets focus on Alzheimer's. Next slide. Train and test splits. 80% of the data was used to train and 20% was to test the model across 4 categories of dementia, Alzheimer's, mild cognitive impairment, and healthy control. Next slide. Methodology. MCON AI is a multilingual conversational AI framework that provides multi-class classification. It allows low-cost early detection as it doesn't require MRI or PET scans, which are expensive. Multilingual conversational datasets are collected from Dementia Bank. Conversational transcripts in English, Spanish, and Mandarin are pre-processed and labeled using OpenAI's GPT-4. Utilizing multilingual BERT (MBERT) model to analyze language patterns to detect cognitive changes, MCON AI classifies patients as healthy, MCI, dementia, or Alzheimer's across languages. Model performance is evaluated by accuracy and other standard metrics. MCON AI also supports cross-lingual early Alzheimer's detection. This means that you can train the model in one language and use it in other languages for detection. This is useful to detect Alzheimer's in low-resource languages. For example, we can train MCON AI in English and test it in Greek, a low-resource language. Next slide. Results. MRI-based models achieve 84% to 86% accuracy for multi-class classification. Single language text models result in 70 to 80% accuracy for multi-class classification. Compared to existing models, MCON AI achieved 87% accuracy on English and 83% average across all languages. This outperforms single language text models and matches MRI-based models in English while remaining competitive across multiple languages. Confusion matrix is a table used to measure how well an AI model is performing. It compares the predictions made by the model with the actual results and shows where the model was right or wrong. For example, in the combined multilingual English, Alzheimer's, the model correctly predicted 214 as Alzheimer's and misclassified 1 as dementia, 2 as mild cognitive impairment, and 3 as healthy control. Similar confusion matrices are shown for B and C. We trained and tested MCON AI on local machine with low compute resources, and based on our experimental results, MCON AI is cost-effective and easily accessible for widespread screening globally. Next slide. These are the references for our research project. Next slide. Thank you for listening.
All right. Thank you so much for sharing. That was a great research project. And now, if you have any questions, please make sure to send them to me on the chat so I can ask them later on. And for the first three presentations, we'll just go straight through them. Maybe have a little intervention in the middle, and um, and then the rest other three can be right after that. And the questions can be asked during the middle and at the end too. But thank you so much for that. Next up, we have Madhav. I heard that Madhav what might have been a little late. So if he's not here, we can actually skip past him and go circle back to him later on. Let me check. Okay, we can go straight to Bhavya then. If you're ready, could you turn on your video and I'll spotlight you?
Am I visible and audible?
Yes.
Okay, cool. Um, so hello everyone. My name is Bhavya Dwivedi, and today I'll be presenting Rethinking Alzheimer's: Evidence for a Vascular Pathogenesis. Traditionally, Alzheimer's has been viewed as a purely neurological disease caused by protein misfolding, but emerging research suggests that vascular dysfunction or damage to blood vessels could be a major factor of the disease. So in this presentation, I will be discussing how Alzheimer's disease originates in the brain. I will then discuss the Hopfield model and its relations to the human memory. And lastly, I will go over what the Hopfield model means for a vascular pathogenesis. Next slide, please. To start, let's look at how the brain structure changes in individuals with Alzheimer's disease. Next slide. Neuroplasticity, which is our brain's ability to form and reorganize connections, declines over time. As memory loss progresses, neural connections weaken, neurons begin a process called programmed apoptosis or cellular suicide, and immune cells contribute to neuronal death. In conclusion, before visible damage occurs, the brain's connectivity is already deteriorating. Next slide, please. One major hallmark of Alzheimer's disease is protein misfolding. Tau proteins are microtubule-associated proteins, or MAPs, that play a crucial role in maintaining the structure and function of microtubules within neurons. Inside neurons, these proteins misfold and form tangles that disrupt neuronal function. Outside neurons, misfolded amyloid proteins accumulate into plaques that block communication and trigger immune responses. Next slide, please. This process resembles prion diseases, where misfolded proteins can infect nearby healthy ones. This then spreads dysfunction across the brain. Next slide. The next stage is mitochondrial dysfunction, when the cell's source of energy stops functioning. Without enough ATP, ATP is the cellular molecule for energy, cells can't perform essential operations, and the buildup of reactive oxygen species, or ROS, causes oxidative stress, which then damages neurons further. This sets up a feedback loop of energy loss and cell death. Next slide, please. Another important thing to consider, although I know there's no information about it here on the slide, is lysosome deacidification. Lysosomes regulate waste products in the cell, making sure that they are disposed of properly. They need a very acidic environment to be able to break down waste. In Alzheimer's, lysosomes lose their acidity due to a malfunction of a proton pump. When this happens, their enzymes stop working, and misfolded proteins like tau and amyloid proteins can't be broken down and therefore start to accumulate. Damaged mitochondria and other waste then stay in the cell, which further adds more stress, and the cell's overall cleanup system just breaks down. This creates even more damage inside the neurons and adds to the cycle of cell death. To talk about hypoxic state is a lack of oxygen, hypoxia, that causes mitochondrial dysfunction. Reduced oxygen delivery then compromises neuronal metabolism. Cells can't make enough energy, which then leads to further mitochondrial dysfunction and eventually neuron loss. This is where vascular health becomes important. Next slide, please. So genetic studies have shown that certain variants of the apolipoprotein E, APOE gene, play a role. This is a gene that codes for a protein that is involved in transporting cholesterol and other fats into the blood and the brain. APOE of epsilon 3 is protective and reduces the risk of Alzheimer's disease. APOE epsilon 3 is neutral and doesn't have any effect, and it's also the most common variant. And APOE of epsilon 4, however, dramatically increases the risk. In fact, it increases the risk by about 4 times. Interestingly, APOE also regulates lipid transport and vascular repair, showing another link between genes and vascular integrity. Next slide, please. At the cellular level, MAMs, or mitochondria-associated membranes, are critical junctions controlling calcium signaling and ROS production. This is a major breakthrough in Alzheimer's studies. It was discovered within just the last decade. MAMs are activated through calcium changes, as their role in the body is, as I said, to regulate calcium levels. When MAMs malfunction, calcium floods the cell, ROS increases, and cellular structures deteriorate. This disruption again connects energy metabolism to vascular and neuronal damage. Next slide, please. Now I'd like to introduce a computational model that offers a new perspective on memory failure, the Hopfield model. This model, which recently won a Nobel Prize just last year, is a type of artificial neural network that stimulates associative memory, how our brains recall full memories from partial cues. Next slide, please. The Hopfield model is a framework that can learn, memorize, and recall patterns. It is a type of artificial neural network that was introduced by John Hopfield in 1982. It functions as a model of how the memory works. Next slide, please. So this is an example of how the Hopfield model functions. If I put in this L shape and instruct the model to memorize it, it will be able to remember this pattern. If I then fill in part of the shape as shown on the right in the right photo and ask it to recall, it would be able to recall the entire shape. Next slide, please. Therefore, it would return this. However, if I were to load it with too many patterns, it could get confused and mixed up, similar to human memory. Next slide, please. The original Hopfield network was dense, meaning that each neuron in the model is connected to every other neuron. However, it is important to note that this is not true in the actual human brain. A newer version of the model is sparse, which means that only a small relevant subset of neurons are active at any given time. The majority of other neurons remain inactive. The system updates itself until it reaches a stable energy minimum, which is a stored memory. The system can then recall that memory and therefore fill in the pattern. However, when connectivity weakens, the system fails to recall stored patterns, just like in Alzheimer's disease. Next slide, please. So how does this relate to Alzheimer's and vascular damage? Next slide, please. Vascular damage changes blood flow, weakening the synapses that memories depend on. As these synapses weaken, the brain begins to act like the Hopfield network. It is unable to recall stored patterns and memories. Small but widespread losses accumulate until the system hits a tipping point, where the network can no longer settle into stable memory states. Just as a Hopfield model fails when its connectivity or energy supply breaks down, the brain's memories collapse when the blood vessels can't deliver what neural networks need to function. Essentially, the Hopfield model predicts that when the brain's metabolic supply is disrupted, memory collapse is inevitable, which then supports the vascular hypothesis of Alzheimer's disease. Next slide, please. So in my conclusion, the Hopfield model supports vascular pathogenesis because it shows how memory failure occurs when connectivity and energy is compromised. It shows exactly what happens when blood supply impairs synaptic connections in the brain. The model and further research suggests that Alzheimer's may not start in the neurons themselves, but in the blood vessels that feed them. When vascular insufficiency reduces energy and oxygen delivery, it sets off a cascade: mitochondrial failure, oxidative stress, synaptic breakdown, and ultimately memory loss. So by rethinking Alzheimer's through a vascular lens, we might unlock new ways to prevent or slow its progression simply by protecting the brain's blood supply. What's next in this research are that people are trying to develop a blood test for Alzheimer's disease that can predict Alzheimer's disease almost a decade in advance by detecting tau proteins in the blood. Next slide, please. Thank you for listening.
Thank you so much. That was a great presentation and very fascinating as well. Um, Again, if you have any questions, please make sure to send them to me in the chat, then we can go over through them all at the end. Next up, we have Delina. If you are ready to present right now, I know it's a little bit early, but we have to skip over Madhav. So, if you are ready, please unmute and turn on your camera, and I'll spotlight you.
Yes, can you hear me?
Yeah. Okay, awesome. 1 second. Please spotlight. Okay, you can start.
Hello, everyone. My name is Delina Merodra, and I'll be presenting my research topic titled From Setback to Growth, How Reflective Writing Shapes Teen Responses to Academic Failure. This project examines how simple writing interventions can influence how teenagers emotionally and behaviorally respond to academic setbacks, something nearly every student experiences. Today, I'll walk you through my research question, methods, interventions, and findings, and discuss what they tell us about resilience and coping in adolescence. Next slide, please. Let's begin with the background that motivated this project. Academic failure is not only a performance issue, it's a psychological and physiological event. It triggers the immediate reaction followed by coping strategies and ultimately long-term emotional and behavioral outcomes. Madeley and colleagues highlight how stress and online learning environments can intensify these reactions, and you can see the infographic on the left. This inspired me to explore whether reflective writing, a low-cost and widely accessible tool, could help students regulate these responses. The basic model informing my approach is failure, then reaction, coping, and lastly, outcome. I wanted to know whether a short writing exercise could shift that cycle toward growth rather than discouragement. Next slide, please. My research question was, how does reflective writing affect adolescent responses to academic failure? More specifically, I investigated 3 sub-questions. Does reflective writing increase persistence on difficult tasks? Second, does it improve emotional regulation after setbacks? And third, does it enhance motivation for future challenges? To examine this, I compared 3 types of writings: narrative, analytical, and neutral. Next slide, please. I proposed differentiated hypotheses for each writing type. First, I examined the hero's journey narrative writing to promote personal growth and motivation. This format encourages students to recast themselves as protagonists overcoming obstacles. Second, I expected learning-oriented analytical writing to help students identify specific strategies for improvement, strengthening their coping skills and focus. Finally, the control group, who wrote about neutral topics, was expected to show the least impact on motivation or emotional regulation. Next slide, please. Okay. Next slide, please. Can you go next slide? Thank you. This study included 34 adolescents aged from 14 to 18. As shown here, the age distribution was fairly even across the grade levels. The participants were divided into 3 groups: Hero's Journey, which was 11 students, the Learning Oriented, which was 13, and the Control, which was 10. Gender distributions were also balanced with about 53% females and 47 males for percent males. This diversity helped ensure that the writing intervention effects were not tied to age or gender and keeping it neutral. Next slide, please. Participants completed an online survey and were then randomly assigned to one of the 3 writing groups. They engaged in a reflective writing task based on their assigned condition, a stimulated academic failure, which involved intentionally difficult math problems meant to induce a little bit of frustration, and a persistence challenge where the problems were hard but solvable, and there was an optional heart rate monitoring to evaluate physiological stress responses. So this design allowed me to measure both emotional and behavioral indicators of resilience. Next slide, please. Each group completed a different writing intervention. Group 1 was the hero's journey, and students rewrote a personal academic failure using the classic plot arc: challenge, struggle, growth, and then return. Group 2 was the learning-oriented reflection, where students analyzed a specific failure and identified lessons, alternative strategies, and future improvements. Group 3, which is the neutral control, Students wrote about unrelated daily life topics serving as a baseline. So this allowed me to see whether narrative, analytical, or no reflection provided the strongest benefits. Next slide, please. Okay. Participants then completed a math challenge designed to induce mild frustration. This included questions like ident- identifying the 23rd prime number, solving train problems, or summing integer sequences. Problems meant to feel hard, and it was also time pressured. Heart rate, heart rate data showed notable differences, such as the hero's journey group peaked at around 110 BPM. The learning-oriented group stayed around 80 BPM, and the control group showed moderate variability from 80 to 92 BPM. Self-reported frustration also varied. The hero's journey group reported mostly 3 and 4s, indicating higher emotional activation. The learning-oriented group clustered around 1 and 3, indicating calmer responses, while the control group showed inconsistent responses ranging from minimal to high frustration. Next slide, please. Next, participants completed a second task, this time solvable but still challenging. This tested resilience and behavior after the failure. Across groups, confidence scores remained surprisingly high. Hero's journey was 5 out of 5. Learning oriented was around 4 or 5, and then control was also around 4 and 5. So heart rates actually decreased slightly during this round, suggesting emotional recovery when students felt more capable and comfortable with the questions. This contrast between emotional and behavioral measures was one of the most interesting results. Next slide, please. Overall, the findings indicate that reflective writing does influence how teens respond to academic failure, but different types of writing influence different dimensions. The hero's journey group showed strong emotional engagement and high motivation. The learning-oriented group showed the most stable emotional regulation, staying calmer after failure. And the control group lacked both emotional structure and reflective grounding. These patterns suggest that writing interventions can shape both short-term emotional responses and the willingness to persist through difficulty. Next slide, please. These results have several educational implications. So reflective writing could be integrated into classroom routines to build students' resilience and coping skills after setbacks. Narrative frameworks may also boost motivation, while analytical writing supports composure and strategy development. However, there were a few key limitations. Heart rate data were kind of inconsistent due to varied devices and environments. The study measured short-term responses, and long-term effects remain unknown. So future work could include both follow-ups and more standardized physiological monitoring. Next slide, please. So to conclude, reflective writing, whether it be narrative or analytical, shows measurable benefits for motivation, emotional insight, and persistence after academic failure. The hero's journey appears to support growth mindset
இதெல்லாம்
thinking.
லேர்ன் பண்ணிக்கோ அந்த மாதிரி பண்ணணும்.
Not like your office.
It's
The
not like your office,
learning-oriented
like
writing
impression.
fosters analytical coping skills.
Lena, you're on mute. Can you unmute yourself? Sorry.
Yes,
Thank
no
you.
problem.
There you go.
Okay. So, the reflective writing, whether it be narrative or analytical, shows measurable benefits for motivation, emotional insight, and persistence after academic failure. The hero's journey appears to support growth mindset thinking. The learning-oriented writing fosters analytical coping skills, and even short-term interventions can still transform failure into an opportunity for growth. This suggests a promising low-cost tool for supporting students' physiological resilience. Next slide, please. And these are my resources. Thank you.
Thank you so much. That was a great presentation. Um, so now we will go into around a 10-minute I guess, break time. During this time, just feel free to get up, do whatever you want, and we'll meet back together at 12:45, or I mean 10:45. So please make sure to be back by that time. But congratulations on everyone who's presented so far. It's been really engaging, and thank you for all of your hard work. All right. Thank you for coming back, everyone. Next up, we have Samian. If you could turn on your video and if you could turn on your camera and your mic, I'll put you on spotlight and you can present your presentation.
Awesome. Thank you. Thank you, Sungwoo. Hello, everyone. Welcome to my presentation on GFAP and NFL plasma biomarkers' association with obesity and metabolic health to predict Alzheimer's disease in HABS HD study participants. So my name is Samian Syed. I'm a junior at Van Nuys High School, and I will be presenting today for the virtual symposium for the USC High School Neuroscience Journalism Club. So again, my mentor is Dr. Sharice Winston, a professor at the USC Keck School of Medicine. Next slide. So first, we're going to go over background for the study, including an introduction to hypotheses, objectives, and biomarkers. Next slide. So firstly, what is Alzheimer's disease? So Alzheimer's disease is a type of dementia that leads to memory loss, cognitive decline, and behavioral changes. It is classified as an irreversible and progressive neurodegenerative disease. Alzheimer's disease operates by degenerating neurons and brain cell connections. Next slide, please. So next, what is GFAP? So GFAP, standing for glial fibrillary acidic protein, is a protein found in astrocytes. Astrocytes are a type of glial cell in the brain, and when astrocytes are damaged, GFAP is released into the blood and cerebrospinal fluid. Astrocyte damage can occur in early neurodegenerative diseases such as Alzheimer's. This means that elevated levels of GFAP can indicate the presence of a neurodegenerative disease such as Alzheimer's disease. Next slide. Next, what is NFL? NFL stands for neurofilament light chain and is a protein found in neurons. So when axonal damage occurs, NFL is released into the blood and cerebrospinal fluid. Axonal damage can occur in neurodegenerative diseases such as Alzheimer's. This means that elevated levels of NFL can indicate the presence of a neurodegenerative disease. However, it is important to take into account external factors that can affect NFL levels, such as age, head trauma, and pregnancy. Next slide. Okay, what are the objectives for the study? Our first objective is to evaluate whether or not metabolic health and obesity interact to influence plasma biomarkers of Alzheimer's disease. The second objective is to examine any associations between the four categories of metabolic health and obesity status with plasma biomarkers independent of race and ethnicity. Now, what are the hypotheses? The first hypothesis is that metabolic health and obesity will interact such that metabolically unhealthy and obese participants will be more associated with adverse plasma biomarker levels than other combinations. The second hypothesis is that the four metabolic health and obesity status categories will display differential associations with plasma biomarkers independent of race and ethnicity, meaning they'll show different associations that can be distinguished when compared to each other. Next slide. So my methodology for this study was participant data of biomarker levels from cognitively and functionally normal patients from the HABS HD cohort. For my definitions of metabolic health and obesity throughout the study, metabolic health was defined using three cardiometabolic risk factors: hypertension, diabetes, and dyslipidemia. Each factor was determined either as present or absent, and a cardiometabolic risk count was calculated as a sum of these indicators. Participants with two or more of these risk factors were classified as metabolically unhealthy, whereas participants with fewer than two were considered metabolically healthy. Obesity was defined as based on body mass. Participants with a BMI greater than or equal to 30 were considered obese, and those with a BMI lower than 30 were considered non-obese. Next slide. Okay, now we're going to move on to the demographics of the HABS HD participants studied. Next slide. So this is quite a large table, but in this demographic table, you can just look at the top parts and you can see that there are 728 total participants who are classified as non-obese, with 412 of them being metabolically healthy and 316 of them being metabolically unhealthy. Additionally, there were 639 participants in total considered obese, and 245 of them were considered metabolically healthy, with 394 of them being considered metabolically unhealthy. The average age of the participants in this study was around 66 years old. Around 2/3 of this cohort's participants were identified as females, whereas the other were males. The average years of education for participants in this cohort was around 13 years. Around 76% of these participants are non-carriers for the ApoE4 gene, a gene increasing the risk of developing late onset Alzheimer's disease, and the other 24% were carriers. So the participants that made up the study were white, Black, and Hispanic. Next slide. All right, next we'll have the results from the HABS HD participants studied. Next slide. So first we have the distribution of GFAP and NFL levels of the participants by obesity status. So as seen in the diagrams, participants who are obese had statistically significantly lower levels of GFAP and NFL in their blood compared to non-obese participants. This result can lead us to conclude that obesity can be correlated with less risk for Alzheimer's disease. And you can see that the orange represents obese participants and is lower than the green, which represents non-obese participants. Next slide. Next, we have the levels of GFAP and NFL in the blood as compared to body mass index. So as BMI increases, GFAP and NFL levels appear to decrease according to the best fit lines of the diagram. This leads us to conclude that the higher the BMI, indicating obesity, the lower the risk for Alzheimer's disease, as these biomarkers correlate with prediction for Alzheimer's disease. And the higher levels of these biomarkers is more adverse. Next slide. So here we have a diagram showing the distribution of GFAP and NFL levels among participants who are metabolically healthy and unhealthy. So the results here show that there's actually no statistically significant difference in the concentration of these biomarkers and metabolic health. So we had a statistically significant difference when it came to obesity. However, for metabolic health, there is not a statistically significant difference. This leads us to conclude that there's no apparent correlation for metabolic health in predicting Alzheimer's disease. Next. So here are some diagrams showing all four of these categories of distribution of GFAP and NFL levels among those who are of different metabolic health and obesity statuses. So these results show that metabolic health does not appear to cause a difference in GFAP and NFL levels, even when compared between obese and non-obese participants. However, obese participants have lower levels of GFAP and NFL when they're metabolically healthy and even when they're metabolically unhealthy. This leads us to conclude that metabolic health does not correlate with predicting risk for Alzheimer's disease, but obesity does, and it predicts lower risk for Alzheimer's disease. Next slide. So these diagrams here show a clear picture of what was described in the last slide. These diagrams show a adjusted level of GFAP and NFL level in participants to show a clearer difference among participants, and this is still an accurate amount of GFAP and NFL biomarkers in their bodies. And it shows that obese participants have statistically significant lower levels of GFAP and NFL compared to non-obese participants. And it also shows that there's little to no difference in metabolic health status in affecting these levels. This again leads us to the same conclusion of obesity being correlated with lower Alzheimer's disease risk, whereas metabolic health has no effect. Next slide. So these diagrams here show the accuracy of GFAP and NFL at predicting all amyloid positivity, a standard biomarker measure used most accurately to predict Alzheimer's disease. These results tell us that GFAP and NFL are around 74% accurate at predicting amyloid positivity. Now, this level is not super high, and percentages that are 80% or higher are accurate, although it is still pretty accurate and it can be worked on in the future. Next slide. Okay, now we're going to move on to the conclusions of the study. Next. So our results seem to disprove hypothesis one, which was that participants who are obese and metabolically unhealthy would have the most adverse results. However, participants who are obese had less adverse results than those who are non-obese, regardless of metabolic health. Our results actually support hypothesis two, which is that there will be differential associations between these biomarkers. As visualized in the results of the study, GFAP and NFL biomarkers did demonstrate differential associations, such as obesity lowering risk for Alzheimer's, independent of racial and ethnic background. Next slide. So according to our results, obese patients had lower levels of GFAP and NFL and considered less adverse levels of these biomarkers. This allows us to conclude that higher BMIs can be correlated with lower risk for Alzheimer's disease. However, all external factors still may be in play. As for metabolic health status in predicting Alzheimer's disease, our results showed no change in GFAP and NFL levels compared to metabolic health status. This allows us to conclude that metabolic health does not correlate with risk for Alzheimer's. Next slide. So finally, according to our results, GFAP and NFL are only 70% accurate at predicting Alzheimer's or amyloid positivity, which is a standard biomarker measure for Alzheimer's risk. Again, this is not highly accurate, meaning that GFAP and NFL are technically not highly accurate measures for predicting risk of Alzheimer's as compared to a standard measure, amyloid positivity. Next slide. So finally, we'll be moving on to the future directions for this research topic. Next. So some future directions I hope to see are investigations into other variables to increase predictive accuracy and determination of the relation between obesity and lower GFAP and NFL levels. I hope that researchers are able to remove the external factors that can still affect GFAP and NFL levels in these studies in the future and are able to focus on only the levels of these biomarkers released through neuronal damage, therefore increasing the accuracy of these biomarkers in predicting the risk for Alzheimer's disease. Additionally, I hope to see future researchers determine why obesity appears to correlate with lower levels of GFAP and NFL in the blood. I hope to see if this correlation is able to determine whether or not obesity is correlated with lower risk and what that means for future determinations of healthiness when considering body mass index and obesity. Next slide. Lastly, here are my references for this presentation on the next slide. Thank you for joining me in this presentation on GFAP and NFL level plasma biomarkers association with obesity and metabolic health to predict Alzheimer's disease in HABS HD study participants. Thank you.
Thank you so much. That was an awesome presentation. Um, and now on to, I think our last presentation should be Shreya. If you could unmute, turn on your camera, and then you'll be good to go.
Hi there.
Uh,
My name is Shreya. I'm a senior from Cleveland, Ohio, and my capstone is Hacking Memory, Neuroethics at the Frontiers of Optogenetics and Engram Engineering. For years, we've struggled with memory-related diseases like Alzheimer's and PTSD, yet the physical workings of memory remained elusive. Now, using cutting-edge light-based technology, we've not only uncovered how memory is stored and activated, but also taken the first steps towards editing, deleting, and even replacing it. Next slide. So the crux of our discussion is something called the engram. Engrams can be hard to picture, but one way to think about them is that every time you encode a memory, different pieces are stored in different brain regions. For example, what you saw in the visual cortex, what you heard in the auditory cortex, how you felt in the amygdala, and how that memory is situated in your life in the hippocampus. Later, when you retrieve the memory, these neurons activate at once as an ensemble or matrix, allowing you to recall a memory. And this coordinated firing is what we call an engram. Of course, this is a really simplified picture. In reality, a single memory can involve tens of thousands of neurons spread across multiple brain regions. But a major question with engrams is like really what part of this finding is novel? What part of like this finding about memory is novel? Next slide. The term engram itself was proposed all the way back in 1904 by German zoologist Richard Seaman, who visualized memory as something that could be encoded, stored, and retrieved, implying like some kind of physical substrate, but there was no proof. In the 1920s, Carl Ashley trained mice to run mazes and then removed different portions of their brain, and found that memory loss depended more on the amount of cortex removed than the location, showing that memory is distributed throughout the cortex. As I explained previously, what you saw in the visual, what you heard in the auditory, etc. So then in 1949, Donald Hebb proposed a Hebbian plasticity, a type of synaptic plasticity emphasizing that cells that fire together wire together. So over time, if a memory remains latent, the Hebbian plasticity of the neurons involved in that engram may decline, causing us to lose certain parts of the memory, for example, forgetting a sound while retaining the visual image. So at this point, the engram theory is gaining traction, and by the 1980s and 1990s, scientists discovered immediate early genes like CFOS and ARC, which turn on when neurons are active. So tagging these genes with fluorescent proteins allowed rough visualization of neurons involved in memory formation, but only in slices or like in small animal preparations. It wasn't until 2007 that Susumu Tonegawa and collaborators at MIT took these techniques further, pioneering the field of optogenetics. Next slide. So far in the 1990s, studies we had, like I said, were only like ex vivo and in vitro. But in Tonegawa's study, we were able to visualize the firing in live mice in live time. So mice were basically placed in a box and classically conditioned using foot shocks to associate the box with the shock. In other words, the unconditioned stimulus was the foot shock, the previously neutral turn conditioned stimulus was the box itself, and the conditioned response was the freezing behavior, which is a fear response. Next slide. After this classical conditioning, just like in earlier studies, the neurons in the DNA gyrus that fired while the mouse was forming this memory expressed the immediate early gene CFOS. But this time, instead of just staining, these neurons were genetically modified to produce channel rhodopsin 2, which is like a light-sensitive switch. The mice were then put in a different safe box, one that wasn't associated with a shock or any fear. And when blue light was shined on the hippocampus, the tagged neurons from context A reactivated, basically, and the mice froze in fear. And this provided causal evidence that the same neurons active during memory encoding are reactivated during retrieval, essentially proving the engram theory. So then in 2013, Ramirez et al. Wanted to see if they could create a false memory in mice. So they tagged neurons that represented a safe box, context A, and then reactivated those neurons with light while giving the mice a shock in a different box, context B. Later, when the mice were put back in the safe box, they froze in fear, showing that the brain had linked the shock to the wrong place and that memory neurons or engrams can be manipulated. Finally, Ryan et al. In 2015 studied whether memories lost due to retrograde amnesia fail to form a physical trace or if the associated engram still exists and can fire but is just inaccessible. So they tagged neurons active during a fear memory, blocked memory consolidation with the drug so mice could no longer naturally recall it, and later used light to activate the initially tagged neurons. When the neurons were stimulated, the mice froze, showing that the memory was still stored in the brain, and repeated activation even restored natural recall, proving that engrams hold memories even when normal retrieval fails. And as the latest advance in optogenetics, this is tremendous, and if applied to humans, it could revolutionize Alzheimer's therapy. Next slide. So this graphic is an excellent summary of how our concepts of memory have evolved, emphasizing the substantive contributions of engram research. So while the old model held that memory formation happens purely in the hippocampus, the engram model suggests that while core details form there, more specific details are stored in a detour circuit, essentially the part of the engram involving other brain regions, like again, what you saw in the visual cortex, etc. So this detour circuit is kind of like RNA. The DNA in the nucleus isn't used like directly each time. Those are like analogous to the hippocampal neurons. Instead, it's transcribed into RNA, which actually carries out the work, which is like the detour circuit. So, in fact, the detour circuit neurons are the ones that are consistently activated when we retrieve long-term and short-term memories, whereas the neurons in the hippocampus eventually go silent and can only be activated under special conditions, as Liu et al. Showed in 2012. So overall, though most of this research has only been done in mouse models, the engram research, it's only a matter of time, like with the rate that science is advancing, before it becomes relevant to humans, raising ethical concerns that we must consider ahead of time. Next slide. Next slide. So memories form the groundwork of identity. Philosopher Derek Parfit's relation R emphasizes that identity is the direct and dynamic sum of our experiences, meaning altering core memories could reshape values, personality, and authenticity. Now, suppressing traumatic memories has been shown to reduce long-term fear response, but this risks overuse and thus the impairment of learning, perception of consequence, and responses to danger. It can also disrupt baseline dopamine levels, fundamentally disrupting the reward pathway. And finally, enhancing existing memories also has risks. Hyperthymesia, or like highly superior autobiographical memory, shows that perfect recall stresses the brain and can actually hinder abstract thinking, while selective forgetting supports creativity. So memory enhancement could reduce innovation and novel thinking. Next slide. We also have to consider autonomy and consent. Autonomy is basically the ability to make informed, self-guided decisions. But in conditions like dementia and Alzheimer's, like we already see family members having to make decisions on a patient's behalf. When patient and then with engrams, like when patients can't remember the very memories on the table for editing, how can they give consent to bring them back? So this is a major threat to autonomy if a surrogate were to make this decision. And also, since decisions rely on past experiences, tampering with them undermines self-governance. Next slide. Another central question is who decides which memories are preserved or erased? In its early stages, memory editing technology will likely be expensive, comparable to therapies like deep brain stimulation that range from $35,000 to over $100,000. If we add costs for viral vectors and molecular tagging that we see with these engrams, this will concentrate access among the wealthy and powerful. And it could be misused to erase memories of corruption, abuses, which really threatens democracy, accountability, freedom, and truth. Next slide. Next, we'll look at interpersonal memory asymmetry and cultural remembrance. So in mass memory modification, truth lies within like the hands of a select few, as we said, the editors, right? So the stress of holding a completely different version of reality from someone else, yet both believing it's true, creates memory pluralism. And on a large scale, this fuels social conflict, uprisings, and the loss of shared history, raising the question like which versions of history will persist, right? And on a smaller scale, philosophers warn that memory pluralism threatens trust, intimacy, and authenticity when people remember different versions of the same moment. Next slide. Looking further ahead, we must also consider commodifications. What starts as a therapy could easily become a market for lab-engineered happiness akin to IVF or plastic surgery. Erasing embarrassing moments or enhancing nostalgia could turn truth into a commodity. Even insurers, employers, and governments might even incentivize interventions. For now, commercialization should be limited to medical conditions like Alzheimer's until ethical frameworks mature. Next slide. Finally, what does this mean for modern law? In a world where memories can be revived or implanted, how do we know if testimony is true? Could courts compel memory retrieval, and would restimulated memories be unbiased? What if someone claims they forgot committing a crime? Are they still guilty? And then would we need new tests to verify whether experiences are real? Finally, some prospects like sanctioned memory erasure for criminals raise deeper issues, undermining guilt, remorse, and rehabilitation, creating a system of ethical instability. Next slide. This brings us to measures being taken in very recent years in preparation for a technology that really has the power to change the world. In 2021, Chile passed a law and constitutional amendment protecting neuro rights and cognitive liberty. The OECD and UNESCO are also working on global initiatives to ensure safeguards as neurotechnology rapidly develops. Scholars like Raphael Yuste advocate for recognizing cognitive liberty as a human right to prevent misuse from brain-based interventions. Next slide. So I'm closing today with a quote by Derek Parfit, which is, "We ought to change some of our beliefs about what we have reason to do. What now matters most is that we avoid ending human history." Next slide. Engram research and optogenetics have revolutionized our understanding of memory, proving that memories are not just abstract ideas, but are physically encoded in neurons that can be turned on, silenced, or even rewritten. These discoveries open incredible possibilities for treating memory-related conditions like PTSD, Alzheimer's, dementia, and amnesia. Yet the same tools that let us restore or repair memory could be used to manipulate it in dangerous ways, implanting false memories, erasing experiences, or reshaping identity itself. The challenge ahead is not just about making optogenetics a technology that offers hope where little existed before, but making sure in the process we don't destroy the very foundations of truth, identity, and what it means to be human. Thank you.
All right, thank you so much, Shreya. That was a great presentation as well.
Thank
Uh,
you.
mhm. Um, so 1 second. Okay. So now we will go into time of quick questions. Actually, Dr. Rust, if you could ask your questions first while I get some things figured out on the meeting side, and then I'll ask some of the questions I got during the presentations, and then after that, that should be it. So, Professor Rust, if you have any questions right now, you can go ahead and ask them right now.
Yeah, you guys hear me okay?
Hmm.
Great. Yeah, all amazing presentations. And yeah, I have like a few questions written down. I also don't want, to take too much of the time. But the first question I would have to the project about speech and AD from Srihit. Um, I'm curious. I mean, it was impressed with it, that they shot there. And honestly, I think also conceptually, it's a really great because we all have like mobile devices. They track our speech with time. So it's yeah, very interesting. I was just wondering, so those data that you got, is this information from the same people or is it always different people? Because I think the ideal case scenario, what you want to have is some sort of changes over time that the AI detects, right? And then it tells you, hey, maybe go to the doctor. to check, some blood biomarkers or whatever to figure out what's going on. So yeah, this would be kind of my first question. And also, do you have any information how far in the disease the people were when they perform these speech assignments? Because what we ideally want to have is like an early biomarker, right? So do you have any information about how early these speech changes can be detected reliably?
For the data sets, I used 8 different data sets. So for each of those data sets, there was different people, but within the data set was the same people. And for when they tested it on like the time scale that you mentioned, they tested for different people at different times. So, like, for example, they tested for a person at when they were a healthy control, but then for someone else, they tested at MCI. So it was different based on that.
Yeah, thank you. That's very helpful. I mean, I really think it's a really interesting approach, and also because it's so cheap and easily available, it's really cool. Do you plan to continue doing just out of curiosity,
Yeah, I plan to
some
continue.
research with that?
Yeah, I plan to continue.
Okay, great. Good luck with that.
Thank you.
Um, Then I had a second question to Samian about the GFAP and the AD data. I mean, it was GFAP and NFL, so like with the biomarkers and obesity. So I'm curious. I mean, it's a really interesting finding, right, with the obesity. And if I remember correctly, there were like some other studies that said actually that midlife obesity is a risk factor for AD. So now I'm wondering, because your data shows a little bit kind of the opposite, but the time point of obesity is for you later, right? So you're basically looking at the late time point when there is also these blood biomarkers. So I'm curious, do you think the time point of obesity could be important and to look at, maybe to ask the people if they were already obese in their 30s or whatever, or if it's something that happened later, if this could play a role in this whole analysis.
Thank you, Dr. Rust. I think that's a really thoughtful and awesome question. So, yeah, midlife obesity is actually a risk factor for Alzheimer's disease. But so with GFAP and NFL levels, it's just that it isn't, and this is likely due to, again, like the timing, like you mentioned. I do think that the timing definitely has something to do with it. The older and older you get, the more, I guess, adverse obesity is. However, it is also important to note that these specific plasma biomarkers don't have the highest specificity accuracy at predicting amyloid positivity. So it isn't fully sure that that these are 100% accurate at predicting Alzheimer's disease. So maybe that it does show a slightly lower risk, but because they're not fully accurate, these external factors that, like pregnancy, like you mentioned, the age. I mentioned age is a big thing, so age could be a definite, impact on these levels. So I think that you're right; it does have to do with timing.
Yeah, wonderful. And I just wanted to add like one detail because I more come from the stroke research area. And so
Hmm.
um, and NFL and GFAP are actually kind of markers of, I would say, brain damage, right? Either it's like from
Hmm.
the astrocytes or from the neurons that kind of go into the blood. So it's I mean, you did already, you thought about it, like how specific it is, but I think kind of delineating brain damage and kind of the Alzheimer's disease pathology could be kind of important. But just, yeah, wanted to give you context that basically those biomarkers actually are also biomarkers for stroke and
Hmm.
damage and stroke. So just important to keep that in mind because I think Alzheimer's is kind of uh, I'm not sure how much, let's say, the blood biomarkers correlate with, the cognitive abilities of the people and so on. So just, yeah, to keep that in mind.
Okay. Thank you. That's awesome insight. I really appreciate it. Thank you, Dr. Rust.
Mhm. Dr. Russ, I'll interject a little bit too. So we intentionally wanted those participants to be cognitively normal, because we wanted to see the predictive ability, but they do so moderate correlation when they are impaired as well too.
Thank you. Yeah, that's super
Mhm.
helpful. I mean, it's really interesting because those biomarkers pop up for basically all neurological, or not all,
Right.
but many neurological diseases. So
Hmm.
it's interesting what the pattern there is, right? And you probably will have groups that have high NFL, but maybe some of the other biomarkers are low, right? And then it's
Right.
interesting to see if there's some of them that are showing like some specifics in the cognitive abilities later on, or they can be predictor of something else. But yeah, great project.
Thank you. Yeah, so we do plan to do a longitudinal analysis to see how those biomarkers are changing because a subset of those participants, like through the collection of HABs and HD, they do transition. They do, they start as cognitively unimpaired and then go to a more dementia-like phenotype. So that would be interesting to see how all those factors and the change in their cognition, does that actually make them more predictive or less predictive?
Sounds good. Thank you.
Thank you for the question.
Okay, if that's all the questions you have, Professor Ross. Actually, Tej Patel, the founder of the USC Journal Club, is here right now, and he can give a little bit of a talk about what this club is and why he started it. And then after that, I have like maybe one or two questions lined up for a couple more of the some of the presentations, and then that should be it for the webinar. But yeah, Tej, you can take it away.
Thanks, Sunwoo. I think even before I kind of go into why I started everything, I just wanted to give a humongous thank you to Sunwoo and also both of the professors for being able to be in charge of the club and everything, and also create this webinar in the first place. This was really excellent. I had an excellent time learning about all of the different presentations. I started the USC Neuroscience Journal Club around, I think, March of 2024 for the sole purpose of finding a community of people that I could explore neuroscience literature and neuroscience research with. This is by far the most interesting thing in the world, in my opinion. This and AI. So I kind of seek two things. I seeked a community, which was the Journal Club, and then I seeked mentors, which was Professor Russell and Russ, and also Professor Winston. So that's kind of the reason why this began in the first place. I passed it over to Sunwoo because I wanted this to continue for the next class and the class after that and everything. So I'm hoping Sunwoo is able to pass this on forward, and we can continually keep growing the club and growing more interest into the brain and neuroscience and everything. I also wanted to give humongous thank you and also congratulations for all the presenters. um, Reading neuroscience literature, especially peer-reviewed neuroscience literature, is really difficult for the first time just due to the immense amounts of jargon, and also just complex neuroscience topics. So for you guys to be able to take what you've learned and digested in the literature and turn that into a presentation that isn't just a repeat of the literature, but that also offers your own opinions and your own thoughts about it, is truly commendable. So congratulations for everyone for basically going through this, learning how to digest a research paper and make a presentation out of it. It's really, really impressive. So yeah.
Thank you so much, Tej. And yeah, shout out to Tej for starting everything. All the members know that it was like, obviously, whether you're new to neuroscience or whether it's like your fifth year doing neuroscience research somehow, neuroscience is a really complex, but it's a really amazing topic. And I'm sure all of us are here for a reason, and that's the reason why, you joined the club, why you did your capstone projects, and why you were able to present at the webinar today. So, yeah, just congratulations to everyone who presented. Thank you, Tej, for starting all of this.
Bro,
And
stop. You guys, I think everyone here should give a really, really great commendation to Sunwoo, because he's the person that was able to direct all of the readings, all of the meetings, all the logistics when it came to presentations, being very um, congruent with me about when stuff was supposed to start and everything. So give a really big grats to Sunwoo for these past few months and everything. Organizing a presentation like this isn't even easy in the first place, bro. So congratulations.
yeah, thank you so much. Um, and like Tej was saying, for next year, there's gonna be like an application for who want if you want to pursue the possibility of being an organizer for this club, like Tej has and like I have, then please feel free to apply because this is something that we both want to continue for as long as possible, and it's just a lot of a thing we see like an exponential growth of potential in. So, thank you so much for everyone who presented today. The one question I did have lined up was for Delina, and Delina had to go leave for like a robotics thing. So I'm just gonna ask Delina about that over like email or something. But yeah, that should be it for the Journal Club webinar. Thank you so much, everyone who participated, came today. Thank you specifically to the professors, Tej, and the speakers today who were able to give such a brilliant webinar and such a great example of just young minds being so motivated and passionate about specific topic that brings progress to, all of us, to humanity. So yeah, again, thank you so much, and you can feel free to leave. Bye bye.